All right, let's try another problem with vector addition and subtraction now. And these are called like riverboat problems. So here's a pretty standard riverboat problem. Let's say that you have a river here, and it's flowing in this direction. And let's say that you are on one shore, and you have a little boat, and your friend is in the boat. Little sailor hat on him. And he's going to go straight across the river to the other side. Okay? Let's put in some numbers. Let's say the stream flows at 5 meters per second south. Okay? Let's say your friend can row at a maximum of 8 meters per second. The question is, if this guy wants to get straight across the river, okay, you can't just like aim for the opposite shore because the current in the stream is gonna like take him down here, right? So we're gonna end up with some direction that's down here. If he just tries to aim for the opposite shore, he's gonna get pushed off course, and his actual direction of travel is going to be down in this direction. Am I right? So what he's actually gonna have to do, what your friend's gonna have to do, is he's gonna have to aim up here somewhere, right? So this 5 meters per south, we need to correct for it. We've got to correct for the current. So in other words, he's going to have to aim his boat in such a way that he kind of travels up here like this, right? And this is the direction that we want to know. So in this type of problem, and I'll write a problem here real quick, that you would get would be something like this. So a person wishes to row across a stream one kilometer wide. He can move in still water at a maximum speed of 8 meters per second. If the river flows south 5 meters per second, what heading should he take? And the heading is just what direction, right? What heading should he take? And how long will it take him to get across the stream? All right. So we sort of covered the beginning of this, right? We sort of drew a little picture, but I'll quickly just redraw it so we can refer back to it. Okay? So let's just, here's our stream. We now know it's 1 kilometer wide. We know we have this flowing like this, and we know that the guy in the boat can travel at, what did I say, 8 meters per second, wasn't it? Yeah, 8 meters per second. Okay. We know that he needs to correct for the stream flow, so he's actually going to aim up here. Okay? So the vector that we end up having to solve from this problem is like this. So he's correcting, he has to go, I guess, against the current, or flow himself, or row himself into the current. So what ends up happening is this, right? He aims up here, okay? This is the way he's rowing relative to the water. The guy on the shore sees him traveling along this way, and I just made a little mistake here in my drawing, didn't I? His speed is actually here. This is where he's rowing in the water, okay? So his actual speed in the direction he's going is going to be a little bit lower than that. Okay? So the first thing we need to solve for is what heading does this guy have to take in order to travel straight across the stream? So just a little aside before we solve this. I've drawn this in the upward direction, but in reality what's happening is this, okay? He's rowing here. The stream is going in this direction, and the straight across is actually the resultant vector, okay, that we're looking for in this problem, okay? So here's, and we'll just label these up. Here's where he's rowing. Here's the angle he's rowing at. Here's the stream. His rowing plus the stream ends up in a resultant that has him going straight across the river, okay? Does that make sense? Now we need to solve first for the heading. So theta is going to be equal to, so sine theta is opposite over hypotenuse, so then the angle should be 5/8. So you get that angle should be about 37 degrees. So this is the heading. Now how would I write that? His heading should be 37 degrees to the north of east, the way we've got this set up, okay? So that's part A. Part B now is figuring out how long it's going to take him to get across the stream. And a very common mistake is taking 1 kilometer, which is the same as 1,000 meters, and simply dividing this into it, dividing 8 into that. But you have to remember, he's not actually traveling across the stream at 8 meters per second, right? He's traveling across the stream at his resultant vector. So whatever this side of the triangle works out to be is how fast he's actually moving from one bank to the other in the easterly direction. So be very careful if you get asked this question not to just blindly throw 8 in there, because you wouldn't end up getting that correct. Okay. So first step, let's just remember the Gorean Theorem here, which is a squared plus b squared equals c squared. And if we look, c squared is always the hypotenuse. There's a squared and there's b squared. So we want to solve for b squared. So we get c squared minus a squared is equal to b squared. Or root c squared minus a squared equals b, which is what we're after. Let's put some numbers in here. 8 squared minus 5 squared, the root of that equals our resultant, or our b value. Or if you want, our resultant velocity. Okay, so you get 6.2 meters per second. 6.2 meters per second is his velocity from the left bank to the right bank. So that's what we deal with in terms of finding his time. So you remember from last year, I'm sure, that velocity equals change in displacement over time. Okay, well now we want time, so time should be equal to displacement divided by velocity. So we've got 1,000 meters, and we're traveling along that 1,000 meter line at 6.2 meters per second, and we should get, I get 161.3 seconds. Maybe better to put that into minutes. About 2.7 minutes, 2.8 minutes. Pretty solid rowing speed, I would say. Faster than I could row.